Today we are going to start another problem, assignment problem, but before going to the assignment problem, let's finish the last lecture's transportation problem. In the last lecture, if you see, we have done some different techniques for finding the optimal solution of the transportation problems and also the different methods, different cases which may occur. We have told that the degeneracy, the solution will be non-degenerate if the number of occupied cells equals m plus n minus 1, m n are number of variables. If this is m plus n minus 1 equals number of occupied cells, in that case the problem is non-degenerate, but if it is not true, in that case the solution will be the problem is degenerate problem. So, first let us see how to handle the degenerate problem. This is the first case. So, let us see degeneracy in TP. Degeneracy in transportation problem. What happens actually, if you see, you have a problem like this, a 3 cross 3. So, if you see, you are having 1, 2, 3 rows and 3 columns, values are 8, 7 and 3, 3, 8 and 9, 11, 3 and 5. The initial basic feasible solution of this problem I am directly writing. Before this, the availability are 60, 70 and 80, whereas it is 50, 80 and 80. The initial basic feasible solution you can obtain as here it will come 60, here it will be 50 and 20 in this column and 80 in this column. So, in this problem, if you see the initial basic feasible solution is this one. Therefore, the number of occupied cells in this case is number of occupied cells, this is equals, if you see 1, 2, 3 and 4, whereas m plus n minus 1, m plus n minus 1, 3 plus 3, 6 minus 1, 5. So, which is not equals to the number of occupied cells, which is equals to 4. So, 5 is not equals to 4, therefore, the problem is a degenerate problem. Once the problem is a degenerate problem, what we have to do? We will allocate a very small positive quantity epsilon in one of the cells, where epsilon, value of epsilon lies between 0 to xij. Epsilon plus 0, we are taking the value of epsilon, small positive quantity, in such a way epsilon plus 0 will be equals to epsilon and xij plus epsilon, this is equals again xij will appear. So, if you see over here in this case, if you see just if you go through this one 0 less than epsilon less than xij, epsilon plus 0 equals epsilon, xij plus epsilon equals xij. So, a very small quantity epsilon has to be added over here. Say in this table, we are drawing the table now in the little bigger form. You are having 3 rows, you are having 3 columns 1, 2 and 3. The values we are writing 8, 7 and 3. So, 3, 8 and 9, 11, 3 and 5, 60, 70, 80 are the availability, whereas demand is 50, 80 and 80. Allocations from the VAM method was here 60, cell 2 1 50, cell 2 3 20 and cell 3 to 80. So, occupied cells equals 4 and which is not equals m plus n minus 1 equals 5. Therefore, what I have to do? I have to allocate a very small positive quantity epsilon in one of the cells in such a way that afterwards it form a loop. So, what I am doing arbitrarily on this, I am assigning a very small quantity epsilon on this. So, once I have allocated epsilon to the cell 1, 2, now if you see number of occupied cells becomes 1, 2, 3, 4 and 5 is equals to m plus n minus 1. So, now the problem is not non-degenerate problem. So, if there is degeneracy at the initial stage like this way, by assigning a small positive quantity to one of the cell, we can make it a non-degenerate cell. So, once we have made the non-degenerate cell, now using the earlier methods, that is, now you have to calculate u I and V j. As you know, u I and V j, this is equals to, should be, I have to calculate it from the occupied cell. So, u 2 plus V 1 equals 7, u 1 plus V 2 equals 7, u 1 plus V 3 equals 3, like this way whatever we have told, you can calculate the value of u I and V j, the method we have defined earlier. I am not talking about that, I am directly writing these values 0, 6, minus 4 and V j will be minus 3, 7 and 3. So, once I obtain the values of u I and V j, now for the unoccupied cells I can calculate delta I j. If you remember, delta I j, this is equals to C I j minus, this is C I j minus u I plus V j. So, for occupied cells, if you see, you will obtain like this. This is minus 5, this is 18 if you calculate, and this one will become 6. So, your delta I j, not delta all delta I j greater than equals 0. In particular, delta 2 2, this is equals minus 5. So, what I have to do? I have to make a loop basically. The loop will be starting from here. I have to assign a small quantity out of these occupied cells, because I will move from here to here like this, then from here to here, then from here to here, again from here to here. The direction would be something like this. So, out of, so this is forming a square side, this is a loop. Now, from the occupied cells, the minimum quantity is epsilon. Since minimum quantity is epsilon, therefore, you can draw again, just I will write down for the loop, you are having 1, 2 and 3. So, here you are having this. So, here your epsilon was there. In this case, what is happening? On this cell, you are assigning or allocating the smallest of the allocated cells. What is the smallest quantity between epsilon 60 and 20? That is epsilon. So, you are allocating plus epsilon here. Once you are allocating plus epsilon here to adjust the row, now from 20 you have to subtract epsilon, that is 20 minus epsilon. So, from here you are going to this direction. Again, to adjust the cell, the column, since you have subtracted epsilon from here, so you have to add epsilon on this particular cell. Once you have added this, you are going like this. Now, you will come here. So, here now this one will be epsilon minus epsilon, epsilon was allocated, and in this direction it is plus epsilon. So, you are adjusting like this way whatever we discussed. So, there will be new allocations now, this epsilon will not be there allocated, whereas in the cell 2 2 epsilon will be allocated, and then it will be 20 and this is 60. So, therefore, your next table, in the next table it becomes, you are having this, you are having 3 rows, values are 8, 7 and 3, 3, 8 and 9, this is 11, 3 and 5, 60, 70, 80, the availability demand is 50, 80 and 80. What are the allocations then? Allocations in the first one, if you see epsilon, this has not been allocated. Here the allocation is 60, here 20, here epsilon will be allocated. So, now the new allocation will be on this cell 1 3 60, on 2 2 it is epsilon, already 50 is allocated in 2 1, then here already 20 is allocated, and here the allocation is 80. So, once I have done this new allocations, again 1 2 3 4 5 allocations are there. Repeat the same process, that is calculate the u I plus V j for the occupied cells. using the formula Cij equals Ui plus Bj for the occupied cells. So, if you calculate the values, you will get the values like this for Ui minus 6, 0, minus 5, whereas for Vj it will be 3, 8, 9. Now, for unoccupied cells, you calculate delta Ij, that is Ci minus Cij minus Ui plus Bj. So, it is becoming 11. For this unoccupied cell, it will become 5, then all these are occupied. Here you are getting 13 and you are getting 1 over here. Therefore, all delta ij is greater than equals 0 for all I and j. So, we obtained the optimal solution. The optimal solution is x 13 equals 60, x 21 equals 50. Since epsilon is 0, so basically nothing has been allocated to this cell. Please note this one. Then x 23 equals 20 and x 32 this is equals 80. And if you calculate the minimum cost will become 750. So, therefore, whenever you are having degeneracy, please note this one from here. Whenever you are having degeneracy, that means number of occupied cells is not equals to m plus n minus 1. You are allocating one small positive quantity epsilon in one of the cells and you are repeating the processes like this, whatever we have discussed. That is another kind of problem which we call as unbalanced transportation problem, Unbalanced transportation problem is what? If you see this thing, you are having only say 2 rows and 4 columns. So, you are having origin 1, origin 2, destination 1, destination 2, destination 3, destination 4. The cost Cij are given like this 90, 50, then 90, 70, after that 100, 130, then 185. The availability is given as 200 here, 100 here, and for this demand is 75, 100, 100 and 30. If you remember, we have told a transportation problem is balanced problem if summation over ai is equals to summation over bj, summation over I and summation over j is coming. Here if you say total availability is 300, whereas total demand is 275 plus 30, that is 305. So, total availability is not equals to total demand. Therefore, the transportation problem whatever we have given here, that is actually unbalanced transportation problem. So, whenever I am having the unbalanced transportation problem, since the availability is less, demand is more, therefore, you have to add one more row over here like this. That is, now you will have 3 rows, 1, 2, 3 rows, number of columns will remain same 1, 2, 3 and 4. Say I am making O1, O2, O3. You are having D1, D2, D3, D4. The costs for these cases are same 90, 90, 100 and 100. It is 50, 70, 130 and 85. For the last column what you do, the cost coefficient Cij you make it as 0 because this is a dummy row you have added, and the in availability on this dummy row you assign 5 units. So, here it is 75, 100, 100 and 30. So, now if you see the total availability and total demand, these are exactly matching. So, once the total availability and total demands are matching exactly, the problem reduced to the balanced problem. So, please note one thing, that whenever I am having a unbalanced problem, in that case your total demand will not match with total availability, either demand will be more or availability will be more. If the demand is more, in that case you have to add one dummy row, and if the availability is more, in that case you have to add one dummy column to make the total available demand and total availability, total demand and total availability should be equal, and you are making it as a balanced problem. Once I have converted it into a balanced problem, then I can solve the transportation problem by the methods we have already discussed. So, these are various cases which may arise in the transportation problem. Now, let us come to the other problem which we call as assignment problems, If you see, an assignment problem is basically a special case of LPP, and in particular if you want to say, I will tell that it is a special case of transportation problem. Here basically what happens, you think about a situation where n workers are there and n jobs are there. I have to assign a worker with a particular job. So, the basically I have to assign one worker with one job only. Please note one thing, that I have to assign only one worker with one worker can be assigned with only one and only one job, not more than one job. So, I have to assign one job to one worker such that the cost is minimized. What can be the cost? Cost may be the cost of the labor, or in terms of time that the worker is finishing a particular job in terms of the time. So, here the cost function may be the actual cost of the labor, or it may be in terms of time also. If you see, we are having one matrix something like this. I am telling this is as a task 1, 2 like this way, you are having n tasks. Similarly, you are having n workers. The associated costs I am writing C11, C12, C1n, C21, C22 and C2n, Cn1, Cn2 like this way, Cnn. If you note here, the availability will be 1, whereas the demand is also 1. Why the availability is 1? Because only one worker can be assigned with one job, not more. One worker cannot be assigned with more than one job, and vice versa, one job can be given to only one worker at a particular time. So, basically our job is to find out which worker should be assigned which job, so that the total cost or time is minimum, so that only one worker, in such a way that each worker is getting only one job at a time. So, if you see in terms of the transportation problem, it is similar to the transportation problem, except that this condition, availability at each source, it should be equals to 1, and this equals to requirement. This is equals to requirement at each destination. So, the only difference with the assignment problem, if you see that the availability should be 1, requirement should also be 1. If you note, these values were different for the transportation problem. So, it is similar to the transportation problem, you can solve it by this. We are assuming that Xij is denotes the assignment of ith worker with the jth job. Xij denotes the assignment of ith worker with the jth task or jth job, such that you can say that Xij will be equals to 1 if the worker I is assigned job j. So, if worker I is assigned the task or job j, then the value of Xij will be 1, otherwise the value will become 0. Okay. And your Cij is the time required, Cij is the cost or time required for assigning ith worker to jth job. So, mathematically if I have to say, I can say minimize z equals summation I equals 1 to n, summation j equals 1 to n, Cij Xij. You are assigning the cost with the assignment of Xij and subject to what? Summation I equals 1 to n Xij, this is equals to 1, j equals 1 to n, and summation j equals 1 to n Xij, this is equals to 1, where your I also will vary from 1 to like this way up to n. So, and another difference is Xij can take only the value 0 or 1 for all I j. So, it is similar to your transportation problem, only difference here is that you are minimizing z equals summation I equals 1 to n, summation j equals 1 to n, C I j x I j subject to summation I equals 1 to n, x I j equals 1, where j is 1 to n, and summation j equals 1 to n x I j, this is also 1, where I is also, that is row wise, column wise, if you take the sum should be equals to 1. So, the mathematical formulation is this one. Now, in various problems it can be applied, just like one we can tell that vehicle routing problem, that is which vehicle should be going to which route, whether it should go through the busy route or it should be going through the least congested route. So, this problem we use the assignment problems. You may think about the timetable problem. In the timetable problem, which class should be assigned or which subject should be assigned to which teacher, like this. The assignment, the bidding problem, that is so many bidders as contractors has bidded for a particular work, for a work or more than work. So, which work should be assigned to which worker. Machine scheduling problem, where you have to schedule the machines so that the cost is optimum. So, in machine scheduling problem and the famous traveling salesman problem, in the traveling salesman problem, of course, I can do it for small number of cities. So, in the traveling salesman problem, which I will discuss afterwards, we can use this particular problem also. Now, related to this, if you see, already we have done the transportation problem, we have done the LPP, still we are trying to find out the alternative ways to find this special kind of problems. In transportation also, you have seen that without using simplex algorithm, by some simple approach, you can obtain the solution of the transportation problem. On the same way, I can solve the assignment problem the way we have written, I can solve the transportation problem, assignment problem using the methods discussed for the transportation problem or using simplex algorithm also. But we will try to find out some easier method for obtaining the solution of the assignment problems also. Let me just quickly go through two theorems. One is the reduction theorem. The reduction theorem says that in an assignment problem, if we add or subtract a constant to every element of any row or column of the cost matrix C I j, then an assignment that minimize the total cost of the original matrix also minimize the total cost of the reduced matrix. Or in other sense, if you see simply, if I have to say, I can tell that you have one cost matrix is given to you, C I j, C 1 1 1, C 1 1, C 1 2, C 1 n, like this way, C n 1, C n 2, C n n. If you add or subtract any element from the row or the column, you will get some alternative or some reduced matrix. Now, the solution of the original problem and the solution of the reduced problem will remain same. Or in other sense, the optimality will not affect if we add or subtract some quantity from here. So, mathematically if I have to say, I can say that for if x I j equals x I j star, suppose this minimizes z equals summation I equals 1 to n, summation j equals 1 to n, C I j x I j, already I have written this. So, summation I equals 1 to n x I j is 1, summation j equals 1 to n x I j, this is also equals to 1. Then x I j star also will minimize the new function, say z new, this is equals summation I equals 1 to n, summation j equals 1 to n, C I j minus u I minus v j into x I j, and of course, these two conditions are there. Summation I equals 1 to n x I j equals 1, summation j equals 1 to n x I j, this is equals also 1. So, z new equals this, where u I j and v I j, these are some real numbers, some real values, positive numbers we take. So, we are saying that if your z is this xij and xij star satisfies z, then it will also satisfy z nu equals this. That means, your cost coefficient has been subtracted by some number. So, how to prove it? If you see from the proof is very clear, z I z nu, this is equal summation over this into xij. So, this you can write down as summation I equals 1 to n, summation j equals 1 to n, Cij xij. This you can write down minus summation I equals 1 to n ui into summation j equals 1 to n xij minus summation your j equals 1 to n vj into summation I equals 1 to n xij. This z nu equals, you can write down this. If you see here, this part summation j equals 1 to n xij and summation I equals 1 to n xij, these values are 1. This value is 1 and also the lower part value is also 1. So, that you can write down this thing z nu equals, you can write down then z nu, this is equals to summation I equals 1 to n, summation j equals 1 to n, Cij xij minus summation I equals 1 to n ui minus summation j equals 1 to n vj. Now, if you see summation I equals 1 to n ui and summation j equals 1 to n vj are independent of the variable xij, because these are some real values, some constant values. So, they are independent of the this one. So, the assignments or the variables that will minimize z will also minimize this z nu also, because xij is ui and vj are not dependent on xij. So, therefore, the xij which satisfies z, they will satisfy z nu also, or in other sense always I can add or subtract some value from a row or from a column. This is the first thing, and second theorem says us that if your Cij is greater than equals 0, such that minimum of I equals 1 to n, summation j equals 1 to n, Cij this is equals 0, then Xij provides an optimal solution. Then Xij provides an optimal solution. So, therefore, if you see here that if Cij greater than 0 such that minimum of summation of this Cij 0, then Xij gives an optimal solution. So, basically using these theorems, these two theorems, we can proceed for the optimality checking or optimal solution of the assignment problem. Before doing this one, let me take one problem and just see in terms of transportation problem how we can write it as this one. So, you have a problem, your tasks is 3 tasks T1, T2 and T3 and 3 workers are there W1, W2 and W3. Values are given like this 9, 5, 8 and 4, 8, 7, 7, 6, 4. So, I have to assign each worker with a particular task. So, I can write it as a transportation problem, just I am giving an example that assignment problem can be solved as a transportation problem also. So, here as usual Xij we are assuming Xij is the assignment of the worker I to the task j, that is worker Wi with task Tj, and Xij equals 1 if worker Wi is assigned task Tj, otherwise the value will be 0. So, what will happen? I have to minimize a z where 9 x 11 plus 5 x 12, you see I am just also multiplying this with the corresponding assignments 5 x 12 plus 8 x 13 plus 4 x 21 plus 8 x 22 plus 7 x 23 plus 7 x 31 plus 6 x 32 plus 4 x 33. So, this you have to minimize the cost from the cost coefficients, you are multiplying by summation I equals 1 to n, summation j equals 1 to n C I j x I j. So, you are getting this subject to the sum of the rows for the elements and the sum of the column of the elements should be equals to 1 only, because availability and demand for each case it is 1. So, basically x 11 x 12 plus x 13 this is equals 1, x 21 plus x 22 plus x 23 this is equals to 1, and x 31 plus x 32 plus x 33 this is equals 1. This is for row wise x 11, x 12, x 13, x 21, x 22, x 23, x 31, 32, 33. Similarly, for column x 11, x 21, x 31, some of them also should be 1. So, x 11 plus x 21 plus x 31 this is equals 1. Then x 12 plus x 22 plus x 32 for the equals 1. This is for the second column, and for the third column x 13 plus x 23 plus x 33 this should be equals to 1, and x I j can take the value either 0 or 1. So, in terms of transportation problem also, if you wish you can find out the solution of this. Now, let us see a mechanism by which we can, by some other comparatively easier technique, we can find out the solution of the assignment problems. You see this one now, the Hungarian method for finding the solution. This Hungarian method was developed by the Hungarian mathematician D. Kong. If you see in step 1, we are telling formulate the cost table from the given problem. Already you have done it. If the table is square, go to step 3, otherwise go to step 2. If it is not square, that means number of rows and number of columns are not same. So, source and destination are same, but I have to assign one source to one destination only. So, in that case, in step 2 we are telling add a dummy source or dummy destination to make the table as square table. The cost elements for the dummy source and destination will be 0. So, if it is not square, then depending upon the problem either add one more row or one more column, and the corresponding cost will be 0, and by adding this dummy row or column you are making the problem as a balanced problem or the problem as a square problem. Number 3, locate the smallest element in each row of the given cost and subtract it from each element of that row. So, find the for the first row, find the smallest element and subtract it from all the elements of the row, and do repeat the case for all the rows, then do the same for each column after row wise subtraction. At the end, what you will get, each row and each column will have at least 1 0, because you are subtracting for each row the smallest element, and similarly for each column also you are subtracting the smallest element. So, basically from theorem 1 we got it that if you add or subtract some element, the property will remain same. The next step is in step 4. In the modified matrix obtained in step 3, search for the optimal assignment as follows. Examine the rows successively, that means first check row 1, then row 2 like this, until a row with a single 0 is found. That means, you check the rows, if you can find a row which has only 1 0, then in rectangle this 0, that is put it in a rectangular box, and corresponding to that 0 on the corresponding column, if any 0 is there, then cross it. What I have written, cross off all other zeros in its column. Continue in this manner until all the rows have been taken care of. Okay. So, basically you are checking, trying to find out a row which has only 1 0. If you find a row like that, encircle it through some rectangular box, and on the corresponding column, if any 0 is there, cross it. Repeat the process again for each column of the reduced matrix also. If a row, then see, if a row or column has 2 or more zeros and one cannot be chosen by inspection, then assign arbitrarily any one of those zeros and cross off all other zeros of that row or column. Now, after inspections, if you find that you are not getting a row or column which has only one 0, but more than one 0, then you can arbitrarily choose any one of these zeros and you can strike out the other zeros, and you are repeating these processes until the chain is completing. Then in step 5, if the number of assignments is equals to n is, then you are obtaining the optimal, you have obtained the optimal solution. N means number of works. So, you have allocated actually n jobs to n workers. So, then you can stop and you got the optimal solution. But if the number is assignment is less than n, then optimal solution has not reached and you have to go to the next step. What is the next step? You draw the minimum number of horizontal and vertical lines to cover all the zeros of the reduced matrix. You can do it by which way? Follow this one. Mark tick rows that do not have any assigned zeros. There may have rows which are not having any assigned zeros. So, in that case you cross it by this way. Then mark columns that have zeros in the marked rows. That is, repeat the cases for this one. Mark the columns again by right sign that have zeros in the marked rows. Number C is, you see, mark the right tick sign rows that have assigned zeros in the marked columns. I will explain this with example. Next, repeat the procedures B and C until the chain is completed. That is, B C means you mark the column and you mark the tick the rows. Then draw lines through the unmarked rows. Please note this one, this point is important. Draw lines through the unmarked rows and marked columns. This gives us the desired minimum number of lines. So, you draw lines through all the unmarked rows, means where you have not ticked, and for column those you have ticked, you draw lines on that. So, for row and column it is different. For row you have to choose unmarked row, whereas for column you have to choose unmarked column. Then after you completed step 6, in step 7 you have to develop the revised matrix, cost matrix. How? Find the smallest element of the reduced matrix not covered by any of the line. So, if you will have cost elements, cost coefficients which are not covered by the line, find out the smallest element among them. Subtract this element from all the uncovered elements, that means where line is not passing, and add that element to all the elements lying at the intersection of any two lines. So, basically you are finding the smallest element, and once you have obtained the smallest element, from the smallest element what you are doing? You are smallest element, you are subtracting it from the uncovered elements, whereas if there is an intersection of two lines, that element, with that element we will add the smallest element. Then again we will go to step 5 and repeat the process. Repeat the process means again you allocate zeros and you repeat the process until we obtain the optimal solution. You see this one. The same problem can be defined like this way. You are starting, the setup cost of the problem is this one. The setup cost table for this, is it a maximization problem? Then you convert it to a minimization problem by subtracting all the elements from the largest element of the cost table. The same thing is true for the transportation problem also. So, if it is a maximization problem, you are converting it into minimization, because the process whatever we are telling, that is for this one. Then is it a balanced problem? If it is no, then add dummy rows or columns, as I have told you earlier. Then obtain the reduced cost table by subtracting smallest number in each row or column, subtract smallest number in each column for every number in that column. Then whether can all the zeros be covered, what I have told in different steps. If yes, then revise the opportunity cost by finding the line, drawing the lines and finding the smallest number of the uncovered elements, and otherwise you find the optimal solution obtained. So, basically through this diagram also we can, through the flow chart also we can show it like this. Now, let us take one example for this one. You see this, a company has 4 machines with which perform 3 jobs. A company has 4 machines which perform 3 jobs with various cost. Each job can be assigned to one and only one machine. Based on the following table, determine the optimal job assignment which minimizes the cost. So, you see, based on the following table, you determine the optimal job assignment which minimizes the cost. So, the function is like this. You have say 4 jobs W, X, Y and Z, and you are having A, B, C. So, which worker should be assigned which job, the corresponding costs are written over here. So, your initial table, I am sorry, not this problem. I will discuss the problem just after some time. Before that, let me take this problem, because I will take that problem after some time. You have say 4 subjects L, Q, D and R. L is LPP, Q is queuing theory, say D is data structure, R is real analysis. We have 4 professors, say A, B, C and D. For associating one teacher with a subject, corresponding costs are given as 2, 10, 9 and 7. For the second row, 15, 4, 14 and 8. C is 13, 14, 16 and 11, and for D it is 4, 15, 13 and 9. So, you have to assign one professor with a particular subject. What is the step 1? I am just writing the steps. So, in step 1 what you have to do? For each row, determine the smallest cost and subtract it from all the elements, as I have told you. So, basically what will happen? You will have this, you are having L, Q, D and R, you are having 4 rows A, B, C, D. So, for the first row you see 2 is the smallest element. So, subtract 2 from all the elements. So, 2 minus 2 0, 10 minus 2 8, then it is 7, then it is 5. Then come to the next row the smallest element is 4. So, subtract again 15 minus 4 11, then it is 0, after that 10 and 4. Similarly, for the third row smallest element is 11. So, it will become after subtraction 2, 3, 5 and 0. In the next one, if you see, lowest element is smallest element is 4. So, subtract 4 minus 4 0, 15 minus 4 11, then 9 and after that 5. So, this is for the row. For each row you are finding the smallest element and subtracting it from the all the elements. In step 2 what you will do? In step 2 now what I will do? I will subtract from all the columns, that is you are having L, Q, D and R. On this side you are having A, B, C and D. Now, for each column from the reduced matrix, not from the original matrix, please note it. From the reduced matrix, for each row you are doing it. For each column you have to do the same thing, find the smallest element and subtract it from the all the elements. So, already 1 0 is there. So, first column will not change, 0, 11, 2 and 0. In the next column also 1 0 is there. So, therefore, this column will also not change. Then you are having next one is 5 is the lowest one. So, smallest element. So, now 5 has to be subtracted from the all the elements of the third column. So, that you will get 2, 5, 0 and 4. Again, if you see the last column, fourth column, 1 0 is there. So, it will remain as it is. So, this is the step 1 and step 2. This is you are doing for all the columns. You have done it for all the columns. So, if you note, each row has at least one row, at least 1 0, just like third row is having more than 1 0. Similarly, each column is having your more than one, at least one 0. Each column is having at least one 0. First column is having 2 zeros, second, third and fourth columns are having the number of zeros are equals to 1. So, let me take the same thing, let me write down into little bigger form. So, this was step 2. You are for each row and column you are subtracting the smallest element for all the from all the elements for that row or column. So, now you are having the problem reduced matrix after subtraction of row and column as 0, 8, 2, 5, 11, 0, 5 and 4, 2, 3, 0 and 0, 0, 11, 4 and 5. So, now you start examining the row. If you remember, we have told you start from the first row, you try to find out a row which has only one 0. In the first row is having only one 0 at the cell 1 1. So, you put it under the rectangular box. Once you are putting it on the rectangular box, on the corresponding column, that is on the first 1 1. So, column is first column, this is 1 0 is there, you just cross this thing. That means, corresponding column you are crossing it, that means this 0 already we have cut, you cannot use or allocate this 0. The meaning is you cannot allocate this 0 again. So, I think it is clear, you are scanning the first row is having only 1 0. So, you are encircling with in a rectangular box and correspondingly on that column if any 0 is there, you are crossing it. So, I have crossed it. Then next one is in the second row is having only 1 0. So, again I am putting it under this box, there is no column in this. In the third row if you see, you are having 2 zeros. Since we are having 2 zeros at present we will not do anything, and fourth row is having no 0. So, now we will scan columns. First column already has been assigned, second column has been assigned, third column is having only 1 0. So, you encircle it corresponding to this 0 on the corresponding row, if any 0 is there then cross it. So, now I have crossed it. So, what is happening here if you see, what is the how many assignments you have done? You have done number of assignments equals 1, 2 and 3, and which is less than 4, the total number of order of the cost matrix. Therefore, the solution, whatever solution you are obtaining, it is not optimal, because you have to assign 4 professors to 4 different subjects only. So, now I have to go to the, since the solution is not optimal, since number of assignments is less than number order of the matrix. So, I have to go to the next step. I have to tick mark now the unoccupied rows. What is the unoccupied row? This was occupied, this was occupied, this already has been done by the column, this is occupied. And corresponding to this, what we have told, you put that right mark on the unoccupied rows, and corresponding to that unoccupied row, if any column is there in a 0, that column you also tick it. So, in this row there is only 1 0 in the column 4 1. So, in column 1 also you tick it, and after that all are occupied or all are given. Now, what you do? After this you have to draw straight line through all unmarked rows. The unmarked rows are which one? Unmarked rows here these two, this is marked. So, unmarked rows in this case, that means you are just drawing a line like this. You are drawing a line like this on the unmarked rows and draw the line on the marked column. You have only one marked column. So, marked column means you are drawing like this way. So, if you see now here, so first note this thing, you are having only, you are marking the unoccupied row, there was only one unoccupied row. So, I have ticked it. Corresponding to this there is 1 0. So, corresponding column also you have marked it. Once you have marked these two, nothing I have to mark now. So, now I have to draw straight line for unoccupied or unmarked rows. Unmarked rows are these two, because for this column there is a mark. So, I will cannot take the first row. So, unmarked row are row 2, row 3 and the marked column is column 1. So, I have draw the straight line. So, what are the unoccupied elements? Unoccupied means which are not passing through the straight line. The elements are 8, 2, 5, here it is 11, 4 and 5. The minimum of these elements is how much? Minimum of these elements is 2. So, what you do now? In this, in the next table, you are having L, Q, D and R, A, B, C and D. So, for the uncovered elements or which are not covered by the straight line 8, 2, 5, 11, 4 and 3. What you do for these elements? You are finding the smallest element is 2. So, subtract it from this, that means it will be 6, 0 and 3 and on this line it will be 11, 4, 5. So, subtract 2. So, 9, 2 and 5 is there 3. Next what we have told, if there is a intersection of two straight lines, then add the smallest element on that particular cell. Intersection here, this is the intersection, this is another intersection, that is in 2 1 there is one intersection, cell 2 1, cell 3 1 there is an intersection. So, you add 2 with 11, that is 13 and for 3 1 you add 2 with this element 2. So, it becomes 2 and all other elements which were marked, keep them as it is, do not change anything. All other elements which were marked by the straight line, keep them as it is. So, it will be 0, 13, 0, 5 and 4 and here it is 0. So, from here you are getting this. Now, what you do? Again assign. In the first case what you see, 2 zeros are there, you cannot assign in the first row. In the second row you are having only 1 0, sorry, this I have not written, 3 0 and 0. Okay. So, I am assigning this. In the third row what is happening? 2 zeros are there. So, I will skip. In the fourth row 1 0 is there, corresponding to this 0 in the corresponding column 1 0 is there, I am crossing it. So, the rows are over. Now, go to the columns. Second column this already assigned, second column assigned, third column 2 zeros I will not touch, fourth column there is only 1 0. So, I will touch it and corresponding row the 0 I will cross it. Now, if you see you are having only one row where you are having this. So, therefore, your assignment will be this. So, now number of assignments are 4. Therefore, you can say that your A to D, B to Q, C to your R and D to L. So, the mechanism is clear. The cost will be the cost corresponding cost of the original problem of this cell, that is A to D. So, it will be 9, A to D is 9, B to Q, Q is 4, that is 9 plus 4. So, it is 9 plus 4, then it is C to R, C to R, C to R is 11 plus D to L, L is 4. So, plus 4. So, the total cost becomes 28. So, like this way we can solve the problem. Just very first let me solve the other problem which I was telling you just now. A company has 4 machines which performs 3 jobs. So, with various cost, each job can be assigned to one and only one machine. Based on this table we have to find the optimal assignment. So, after I have made all these things, so after row deduction, and if you see here one thing is there, it has only 3 rows and it has 4 columns, 3 rows and 4 columns. So, it is not balanced. So, therefore, you have to add one dummy row over here. I am just writing like this. Okay, let me write here. So, there will be now 4 rows because you are having 3 rows. So, it is not a square. So, add one more row, you are having sorry W x y z 18, 24, 28, 32. So, 8, 13, 17, 19, 10, 15, 19 and 22, and for the dummy row the cost will be zeros, all zeros. So, this is now table, since it was not balanced, the cost matrix was not square. By adding one row you are making it a square matrix, or if required you can make it a column. So, now what you have to do, you have to first for each row subtract the smallest element from all elements, for each column subtract the smallest element from each element. If you perform this, then you will obtain a table like this. You are having, I am just writing at a time 0, 6, 10 and 14, 0, 5, 9, 11, 0, 5, 9 and 12, 0, 0, 0 and 0. Please note this one, after making the row reduction and column reduction we obtained this one. So, now start assigning. For the first row only 1 0, so you are doing it. So, on the corresponding columns you are deducting this. Next row no 0, next row no 0, next last row no 0, come to the columns. First row already assigned, second row is this. So, corresponding zeros you cut it. So, therefore, you are having only this one. So, again you have to repeat the process, I am just telling this one. So, only 2 assignments are there, although there are 3 jobs are there, 4 jobs are there. So, what are the unmarked rows here? Unmarked rows here, sorry, these 2, and corresponding to these 2 you are having a marked column. So, now you can assign, you can draw a line from here, you can draw a line from here, you can find out the smallest element from here, the smallest element is 5, and you can repeat the process. I think in the same way you can, smallest element is 5, so you can subtract from here, and after that in the intersection, that is on this you can add this, that is you will get a table like this. It will be 6 minus 5. So, in these cases it will come 1, 5, 9, 0, 4 and 6 and 0, 4 and 7, whereas there is only one intersection at this point 4, 1. So, this value will be 5, all others will remain same. So, 0, 0, 0 and 0, 0, 0. So, if you repeat the process, then you will obtain the solution. By the same way, I am just writing what can be the possible solution. There is one beauty, the beauty is you can check it of your own. You can get 2 different assignments. By considering 1 0 at a time, you will get one solution as this, and if you consider other type of assignment, you will obtain this kind of solution. But in both case, your optimal cost will be equals to 50. So, you can check it of your own. I think it is understandable. Thank you.